Uh, Hello everyone. So today's topic is relations and functions. So in this lecture, you will learn about how to link pairs of objects from two sets, and then introduce a relation between the two objects in the pair. So you will learn how to link pair of objects from two sets, and then introduce a relation between the two objects in the pair. Introduce the relation between two objects in the pair. Second, you will also learn about the spatial relation that qualify to be a function. About spatial relations that qualify to be a function. So, our first topic is Cartesian product of two sets. Cartesian product of two sets. So, if we have two non-empty sets uh, given two non-empty sets P and Q, then the Cartesian product P into Q is the set of all the ordered pairs of the elements from P to Q. That is mathematically P cross Q is in set builder form we can write it as PQ followed by a semicolon where P belongs to capital P and Q belongs to capital Q, where P and Q are non-empty sets, and small p and small q are the elements of the set P and Q. For example, let's say P have 1 and 2 element, and Q set has 3 and 4 elements, and then P cross Q will be 1 comma 3, 1 comma 4, 2 comma 3, and 2 comma 4. So here is a note. If either P or Q is a null set, then P across Q will also be an empty set. If either P or Q is a null set, then P cross Q will be empty set. That is P cross Q is equal to phi or empty set. So for example, P is 1 comma 2 and Q is an empty set, or we can say phi. So P cross Q is equal to empty set. of I. Second point is, uh, like in set, order is not important, but in Cartesian product of two sets, order is important. So here order is important, or we can say very crucial. Example, if P is a set 1 cross 2 and Q is a set 3 comma 4, then P cross Q 1 comma 3 and 1 comma 4 and 2 comma 3 and 2 comma 4. So in this example, if we take 1 comma 3, then this pair is not equal to 3 comma 1. Also 1 comma 4 is not equal to 4 comma 1, and 2 comma 3 is not equal to 3 comma 2, and 2 comma 4 is not equal to 4 comma 2. So order is very important when we deal in Cartesian product of two sets. So from the above example, this implies that if we change the order, then it will change the meaning of the relation or Cartesian product. That is, if P and Q is a one Cartesian product and Q into P is a second Cartesian product, then P cross Q is not equal to Q cross P, because order is important. Second, when we define Cartesian product, then the relation between the element is unique. Between the element of ordered pair is unique. So this was about Cartesian product and its properties. Next we have some points to remember. First, two ordered pairs are equal. Two ordered pairs are equal if and only if the corresponding first element are equal and the corresponding second elements are also equal, and second element are also equal. Second, if there are p elements in A, if there are p elements in set A and q element inside P, then there will be P into Q elements in A cross B. So for example, for example uh, if A is a set which contains 1 and 2 element, and B is a set which contains 3 and 4 element, then we have NA is equal to 2 elements and NB is equal to 2 elements. So A cross B should have NA into NB elements is equal to 2 into 2, that is 4. Third point, if A and B are non-empty sets, and either A or B is an infinite set, then A cross B is a infinite set. So if A is 1 comma 2 finite set, and B is a set of natural numbers 1 comma 2 comma 3 3 dots is an infinite set, then A cross B will be 1 comma 1 comma 1 comma 2 comma 1 comma 3 dash dash dash. It is also an infinite set. Fourth point, if A is a set and A into A is defined by A comma B comma C semicolon A comma B comma C, which belongs to set A, where A, B, C are elements of set A. So here A comma B comma C are called ordered triplet. So for example, if P is equal to 1 comma 2, then P cross P is equal to 1 comma 1 comma 1 and 1 comma 1 comma 2 and 1 comma 2 comma 1 and 2 comma 1 comma 1 2. So this is the ordered pair of set P, ordered triplet. So next topic is relations. So what is relation? Relations are a subset of Cartesian product of two sets P and Q. Relations are subset of Cartesian product of two sets P and Q. So if we have P is equal to A comma B comma C and Q is another set which contains Ali, Bhanu, Binoy and Chandra and Divya, or we can write it as A, B, uh, B dash, C and D. So, so this is a set P and Q. So from this we define a relation from P to Q. From this we define a relation from P to Q, P to Q, that is R, and we know that every relation is unique. So this is a unique relation from P to Q where X and Y are elements of this relation, and X is the first letter of the name Y, where X belongs to P and Y belongs to Q. So this is a relation which is a subset of Cartesian product of P and Q. So if we write a relation, then we get A for Ali, B for Binoy, again we have B for Bhanu, C for Chandra. That's it. So because X is the first letter of the name Y, so here we take A and then we take Ali, and B for Binoy, B for Bhanu, and C for Chandra. So this is how we define a relation. Uh, so there are some more definitions related to relations. So some definitions, relations. So a relation R from non-empty set A to non-empty set B is a subset of a Cartesian product A cross B, which we have already discussed. A relation R from a non-empty set uh, to a non-empty set B is a subset of the Cartesian product of A cross B. Second, the subset is derived by describing a relationship between first element and second element of the ordered pair in A cross B. The subset is derived by describing a relationship between first element and second element of the ordered pair in A cross B. Third, the second element of is the image of the first element. In every relation, second element is an image of the first element. So now we define what is a domain, and what is a range, and what is a codomain. So what are domains? So set of all the first elements of the ordered pairs in a relation are set of all the first element of the ordered pair in a relation are from a set A to set B is called domain of the relation R. So if we have A is 1 comma 2 and B has 3 comma 4, and in some relation from A to B we get R is equal to 1 comma 2 and 1 comma 4. So here in this relation domain is 1. So next we have what is a range. What is a range? So set of all second element in a relation R from set A to set B, from set A to set B is called range of relation. So if we have the above example, R is a relation where 1 comma 2 and 1 comma 4 are the ordered pairs, and we have a domain is 1, so our range is 2 comma 4. So whenever we define a relation, we have first element is a domain, so we have a common element 1, so we write it only once. So domain is 1 and range is the set of all the elements in the ordered pairs. So 2 and 4 are the only second elements in the ordered pair. So 2 and 4 is the range of the given relation. Next we have what is a domain. What are codomains? So codomain is set of all the elements in set B. Set of all the elements in set B. So if we have A is 1 comma 2 and B is 3 comma 4, then we have a domain, we have codomain is all the elements of set B 3 comma 4. So here codomain is all the elements of set B 3 comma 4. So codomain is 3 comma 4. So this whole set B is a codomain. So whenever we write a relation from any set to another set, like such as P to Q or A to B, then this second set will be the codomain of this relation. Next we have how to represent a relation. How to represent a relation. So we have first, a relation is represented in rooster form or set builder form. So we have rooster form. rooster form or set builder form. Second, we have visual representation. Like arrow diagram. So if, for example, if we have A is 1 comma 2 and B is 3 comma 4, then from arrow diagram we can draw it like this. This is set A, and when we have a relation from A to B, before drawing a arrow diagram we should have defined a relation. So this is A to B. This is a set B, so it contains 1 and 2 element, and this is set P which contains 3 and 4 elements. And according to our relation above, we have ordered pairs 1 comma 2 and 1 comma 4. So we will match the pairs 1 comma 3, 1 comma 3 and 1 comma 4, where whole set B is a codomain, and this relation is a range, and this element is a domain. Another example, where A is equal to 1, 2, 3, 4, 5, 6, and we have a relation from A to A, that is x comma y, where y is equal to x plus 1. So we can write relation as follows. We have 1 comma 2, 2 comma 3 and 3 comma 4 and 4 comma 5 and 5 comma 6, and that's all. So this is a relation from A to A where y is equal to x plus 1. So here, if we represent it by arrow diagram, this is set A and this is set A, which contains 1, 2, 3, 4, 6, 1, 2, 4, 5, 6. So we have 1 to 2, 2 to 3, 3 to 4, 4 to 5 and 5 to 6. So here this set A is codomain, which is equal to 1, 2, 3, 4, 5, 6, and this relation is a range which is equal to 2, 3, 4, 5 and 6, and the codomain is set of all these elements 1 to 5. Domain is 1, 2, 3, 4, 5. So next we have how to find a number of relations. So the total number of relations that can be defined from a set A to set B is the number of possible subsets of A cross B. The total number of relations that can be defined from a set A to set B is the number of all the possible subsets of A cross B. All possible subsets of A cross B. So if we have n number of elements in A is P and number of elements in set B is Q, then number of elements in A cross B is P into Q. So total number of relations in set A cross B is total number of possible relations is equal to 2 raised to the power PQ. This is the total number of relations when we take a Cartesian product of A cross B. For example, A is a set 1, 2 and B is another set which contains 3, 4. So we have 2 elements in this and 2 elements in this. So A cross B will have 2 into 2, 4 elements. So number of possible relations will be equal to 2 raised to power A cross B, which is equal to 2 raised to power 4 is equal to 16 relations are possible. Next we have functions. So a relation f from set A to B, a relation f from a set A to B is said to be a function if every element of set A has one and only one image in set B. So mathematically, if f is a function from A to B and A comma B belongs to f, then f of A is equal to B, where B is the image of the image under F. B is image under F and A is pre-image of B under F. Pre-image of B under F. So next we have which relations are not functions. Which relations are not functions? First, no two distinct pairs should have the same first element. No two distinct pair have the same first element. For example, we have 1, 2 and 1, 3. This is a relation, a random relation. So 2, 3. So in this we have 1 as an element same element in two distinct ordered pairs, so it is not a function. And we have 2 as a same first element in two ordered pairs, so it is not a function. Second, we have every element in set A should have an image in set B. For example, A is equal to 1 comma 2 and B is equal to 2. So we have a relation where from A to B where y is equal to x plus 1. So mathematically we can write 1 comma 2 is the only relation. So we can see that one has an image in image S2. So if we draw it like this, this is B, 1 2 and this is 2. So one has an image in set B, but 2 has no image in set B. 2 has no image in set B. Therefore this is not a function. Next, so we have some functions and their graphs. Some functions and their graph. So first is identity function. So its graph will be like this, where f of x, so this is f of x and this is x is equal to x, and its domain is real numbers and its range is real number. Second, we have a constant function. So its graph will look like this. So this is a point C and we have x-axis and this is f of x. So it is a function which is defined as f of x is equal to C. So its domain is R and its range is C, where C is any constant. C is any constant. Third is polynomial function. So polynomial function where f of x is which is a general form of polynomial equation a naught plus a1x plus a2x square plus a3x cube dash dash an x n, where n is greater than 0, that is non-negative integers, non-negative integer. So polynomial is so a function is called a polynomial if n is a non-negative integer. If n is not integer, if n is not an integer, then f of x is not a polynomial function. So How to plot the graph of polynomial function? So the shape of the polynomial function, shape of a polynomial function depends on the value of n, where n is greater than 0 and non-negative integer. So we have some examples of a polynomial function and their graphs. So first is f of x is equal to x square where n is equal to 2. So its graph will look like this. So this is f of x and this is x. So its domain is R and range is R, positive real number, R positive. Second graph is f of x is equal to x cube. Also in this f of x square, this graph is symmetric about y axis. Symmetric about y axis. So this is a y axis and this is a x axis. So this is x cube. So its graph will look like this. This is y, this is x. So its domain is real numbers and a range is real number, and it is symmetric about origin. It is symmetric about origin. Next we have a rational function. So what is rational function? Any function in the form of p and q or f of x upon g of x, where g of x is not equal to 0. So this is a rational function. For example, f of x is equal to 1 by x. So its graph will be like this. This is y, this is x. So its domain will be r minus 0 and range is r minus 0, where x is not equal to 0. Next we have modulus function. Modulus function. So it is denoted by mod x, and its graph will is so this is a straight line. This is y, this is x. So its range domain is r and range is r positive real number, positive real number. So we can also write this function as in a piecewise form. where x is positive when x is greater than 0 and x is negative when x is less than 0. Next we have a signum function. So in this we have a function f of x where f of x is 1 when x is greater than 0 and f of x is 0 if x is equal to 0 and f of x is minus 1 when x is less than 0. So graphically we can plot this graph as f of x is 1, minus 1 and 0. So when x is greater than 0 we have f of x is 1. So this will be a this will wait so this is a graph. So this is a hole at 1 and minus 1 and this is solid at 0. So we have f of x equal to 1 when x is greater than 0 and f of x is 0 when x is 0 and f of x is less than 0 when f of x is equal to minus 1 when x is less than 0. So this graph will look like this. Its range is, its domain is R, real number, set of all real numbers, and range is minus 1, 0 and 1. Next we have greatest integer function. So it is denoted by x in square brackets, and its domain is all the positive real number, all the real numbers, not positive, all real numbers are, and its range is integers. So the plot will look like this. So this is y-axis and this is x-axis. So we have 1, 2, 3, minus 1, minus 2, minus 3, 1, 2, 3, minus 1, minus 2. So when x is between 0 and 1, so the value is 1, value is 0. So there is a hole at 1. When x is between 1 and 2, then f of x is 1. When f of x is between 2 and 3, then f of x is 2. Likewise, when x is between 0 and minus 1, then f of x is minus 1. So when f of x is minus 1 to minus 2, we have minus 2. When f of x is minus 3 to minus 2, we have minus 3. So for example, if x is equal to 1.2, so mod x will be equal to 1. If x is equal to minus 1.2, then greatest integer function of x will be minus 2. So this was about some functions and their graphs. Next we will look at algebra of the real functions. Algebra of real functions. So first we have f plus g of x is equal to f of x plus g of x. Second, f of minus g of x, then f of x minus g of x. Third, alpha f x. So alpha f of x. So this is addition, this is subtraction, this is multiplication by a scalar, multiply the function by a scalar. Fourth, we have multiplication of two functions, which is given by f of x dot g of x, multiplication of two functions. And next we have quotient of two functions, f by g of x is equal to f of x upon g of x, where g of x is not equal to 0. So this is a division of two functions, For example, f of x is equal to x square and g of x is 2x plus 1. So first we will take addition operation. So we have x square plus 2x plus 1, which is equal to f of x plus g of x. Second, we have subtraction. So x square minus 2x minus 1, which is equal to f of x minus g of x. Third, we have multiplication by a scalar, multiply by a scalar. So if we multiply function f by any scalar a or equal to 3, so we have 3x square, or if we multiply 3 by g of x, then we have 2x plus 1. Fourth, we have multiplication of two functions, so f of x into g of x is equal to x square into 2x plus 1. This is equal to 2x cube plus x square. Last, we have division. Where f of x upon g of x is equal to 2x plus 1, where 2x plus 1 is not equal to 0 or x is not equal to minus 2. So we can also reverse the operations like g of x by f of x. According to our convenience, uh, we can change the functions and their operations. So this was about relations and functions. Thank you. Hope you like it.